algebra. I'm not there today, and here's your lesson via recording. Hope everything goes well. It's pretty late here as I record, but I appreciate your patience. Lesson 9, Interpreting Exponential Functions. So first of all, let's talk about equivalent or not. Lynn and Diego are discussing two expressions, x squared and 2 to the x power. Lynn says, I think the two expressions are equivalent. Diego says, I think the two expressions are only equal for some value of x. What do you guys think? Are these equivalent? I don't think so, but why? First of all, if I look at x squared, let's see, need a pen. It's really equal to x times x, because we learned if we have the same base with powers, we add the powers, right? That's what we get. Now if we have 2 raised to the x power, that's an exponential function. I can't even split it up into two things like I did the x. But let's try this. If I try to evaluate those, say x evaluated at x equals 1, I get 1 squared, which is 1 for the first function. The second one, I get 2 raised to the 1 power, which is 2. If I try x equals 2, I replace it for the x squared function. I get 2 raised to the 2 power, 2 raised to the second power, which is 4. If I put that in for the other function, 2 raised to the second power, ooh, that one is equal. Okay, let's just try x equals 3. I get 2 raised to the third power, which is 8, and 2 raised to, oh, hold on. I got ahead of myself. I'm not going to re-record it. I'm just going to have you learn from my mistakes and fix it. If I put that into the first equation, I get 3 squared, so sorry, which is 9. I put it into the second equation, 2 to the third power, which is 8. Sorry about that. So yeah, I guess Diego says the two expressions are only equal for some values of x. It would be equal for x equals 2. But Lynn says the two expressions are equivalent, which is not correct. I believe that's the x equals 2 is the only one that it would work for. Okay. I'm staring at it now. How about x equals 4? If I put that into the first equation, 4 squared is 16, and then here we have 2 to the 4th power, which is also 16, and that's it. Promise. Those are the only two values of x that they're equivalent for. Moving on. Alright, so cost of solar cells. So the cost in dollars to produce 1 watt of solar energy is a function of the number of years since 1977. From 77 to 87, the cost could be modeled by an exponential function f. Here's the graph of the function. So let's just look at this a little bit. I have years since 1977, so that's why we're starting here at 0. So this is 1977. So we have 1979, 81, 83, 85, and 87, okay? I don't need any of those marks there anymore, but just showing you that is the years since 1977. On the y-axis, I have dollars per watt. So it costs a lot of money. When we begin, that's our vertical intercept, and the amount of money it costs decreases and then slows down and decreases. It'll never get to 0. It's never going to be free. Okay, let's see what our questions are asking. What is the statement f of 9 is approximately 6 saying about this situation? Well, this right here is t And this would be our y-axis, which is dollars per watt. So f of 9 equals 6, or is approximately 6, would be at 9 years after 1977, which is 1986. The cost in dollars for 1 watt of solar energy was about $6. If I look at number 2, that was number 1. If I look at number 2, what is f of 4? If I look here, I hit there and I come over and read it. It is, let's see, that is in 22, 4, 6, 8, nope, 25, 30, that's about 25. That'd be $25 per watt. And then we have f of 3.5. Let's see, that would be 3.5 about right there. Hits, comes on over, that would be about 30. So at 3.5 years after 1977, it's $30 per watt. Cool. These values represent the cost in dollars of 1 watt of solar energy in 1981 and halfway between 1980, or halfway through 1980, between 1980 and 1981. Okay, let's see, number 3. That asks, when f of t equals 45, what is t? Let's see, 45 would be about right there. Boom. Come on down. That would be about 2 years after 77. 79. The cost of dollars of 1 watt of solar energy was $45 in 1979. And then number 4, by what factor did the cost of solar energy change each year? We're going to have to do some division. So remember, we go up. I have 60 over 80, which is 6 over 8, which is 3/4. So I believe my factor is 3/4, or you could say 0.75. And let's just check it. I'm going to go here. Let's see, I'm going to have, that was 45 over, oh, that's not an easy one to read. Hold on, I can't see it anymore. That's not that awful to read. That would be about 35, and it's going to be off a little bit. Oh, that's backwards too. Again, I'm messing up, but I'm not going to re-record it because we can learn from our mistakes. So we take about 35 over about 45, and it should be close. Yep, 0.778. I didn't read the graph very well, so it's close to 3/4. Okay, we're going to go with the one where we could read the graph much better, and our factor is about 3/4. Cool, moving on. Paper folding. We should try this in class sometime. Do you guys agree? The thickness T in millimeters of a folded sheet of paper after it's folded n times is given by the equation T equals 0.05 times 2 to the n. What does the 0.05 represent? That would be my initial thickness. And I would believe that would mean with no folding, right? Our initial thickness. You could say that is like, that's how thick the sheet of paper is. Next question. Using graphing technology, graph the equation given. Okay, hold please. Okay, I'm going to get a new sheet and show us that graph. I didn't really talk. This initial thickness was in millimeters. I don't know if I said that. I can't remember. So let me get that graph in here. All right, there's our graph. Now the question it's asking us is, how many folds does it take before the folded sheet of paper is more than 1 millimeter thick? Get a pen. Here is 1 millimeter thick. Hits the graph about there. So not many folds. It looks like I have 4 folds is 1 millimeter. So I can't do, well, 4 folds isn't 1 millimeter. So we're not quite there yet. Can't do 4.5 folds. So it looks to be that we need 5 folds for it to be more than 1 millimeter thick. That's it, 5 folds. Let's see the next question. You have it in front of you. How many folds before it's more than 1 centimeter thick? I didn't put that on a graph. I sort of stopped at what you see there is 2, but 1 centimeter thick would be, I'm looking at the graph, sorry, 8 folds. Okay, 8 folds would be more than 1 centimeter, which is 10 millimeters thick. We should try that. You guys want to try that? All right, let me get back to the questions. All right, the area of a sheet of paper is 93.5 square inches. Find the remaining visible area of the sheet of paper after it's folded in half once, twice, and 3 times. So my initial area, and I'm going in half to a variable. Let's see, we have that as times area. That should be in lowercase a. And that should be an N. Sorry, didn't read ahead, did I? Alright, so find the remaining visible area when it's folded in half once. So that would be 93.5 divided by 2. So once would be 46.75 inches squared. Twice, it's going to divide by 2 again. 23.375 inches squared, and then fold it in half again, so I'm going to divide it again. 11.6875 inches squared. So my equation, what I'm doing there is right here. Okay, I can test it by saying n equals 3. I'll type into my calculator 93.5 times 1/2 to the 3rd power, and that would give me a. Let's just test it. 1/2 raised to the 3rd power, and I get 11.6875. Sweet. Using graphing technology, graph the equation. You guys can do that if you'd like. I'm going to start up here at, that would be 100, would be just shy of 100 at 93.5, and cut it in half for 1 fold, 2 folds, cut it in half again, 3 folds, etc. Never reaching 0. Okay, need another sheet of paper because I ran out, and we'll answer those last 2 questions. That last question, sorry. In this context, can n take negative values? Nope. When it's the number of folds, I don't know how to go negative. It's always going to be a positive number. And then the last question, can A take a negative value? A is area. I don't know how to get area negative, so it'll always be positive. All right, the last part of your lesson was something that we were going to do in groups, which is really hard to do with problem cards and data cards. So I'm going to save that for Monday. Good job.